Let us talk about this problem. We are given an array and an integer k. We need to find out maximum of every subarray of size k. Please note that k is smaller than or equal to size of this array. So we have this array and k is 3. So what is the maximum of first subarray of size 3? It's 10. So our first output is 10. What is the maximum of next subarray of size 3? 12. So our next output is 12. What is the maximum of next subarray of size 3? 15. What is the maximum of next subarray of size 3? 15 again. What is the maximum of next subarray of size 3? 15. How many subarrays we will have if n is size of our input array? We are going to have n minus k plus 1 subarrays. So for n size input and k also as input, we are going to print these many things in output. For example, n here is 3 plus 3, 6 plus 1, 7 and k is 3. So we are going to have 7 minus 3 plus 1 elements in the output, which is 5 elements. Let's see this example. The maximum of first k elements is 20. The maximum of next k elements is 8. The maximum of next k elements is 15. And how many elements we are going to print in output? 6 minus 4 plus 1, 3. Now please pause this video and try to write down a function that takes an array as an argument, k as an argument, and prints n minus k plus 1 required integers. Let us first talk about the naive solution to solve this problem. The time complexity of the solution is big O of n square. And the idea is really simple. We consider all subarrays of size k, and for every subarray, we traverse through all the k elements of it and find the maximum of the k elements and print it. To consider all subarrays of size k, we run a loop from I equal to 0 to while I is smaller than n minus k plus 1. These many subarrays we are going to have as we discussed earlier. So we begin with I equal to 0, right? And we run a loop that finds the maximum of these three elements if k is 3, right? So what we do, we initialize the max as 10 and then we run a loop for j equal to I plus 1 to j is smaller than I plus k, right? And inside this loop, we compare every element with the current max, and if the current element is greater, then we update the max, right? So for I equal to 0, we are going to have the max as 10 itself. Now we run the loop for I equal to 1. For I equal to 1 means this window. And inside this window, we again initialize the max as 8. And then we compare the max with remaining two elements. And we are going to have max as 12. And we are going to print this max. For I equal to 2, we are going to initialize our max as 5. And then we are going to compare this max with 12 and 15. That's what we do. We begin with I plus 1. And we run a loop while j is smaller than I plus k. And inside this loop, we compare array j with max. And if array j is greater, we update the max. So for I equal to 2, we are going to have max as 15, right? We are considering this subarray for now. Next time we consider the next subarray and we initialize the max as 12 and we find out the overall maximum as 15. So we print the max as 15. In the next subarray, we initialize the max as 15 and find out the overall maximum. So for I equal to 4, our max is going to be still 15. So that's the output for this particular naive solution. That's how it works. Its time complexity is big O of n square. Now please pause this video again and think of a solution which is big O of n. Let us now talk about the efficient solution to solve this problem. The idea is to use a DQ data structure. DQ stands for doubly ended queue. It allows you to insert elements at both ends and delete elements from both ends. You can insert at the beginning, you can delete from the beginning, you can insert at the end, and you can delete from the beginning. A DQ can be implemented using either a doubly linked list. In doubly linked list, you can maintain a tail pointer and you can do deletions and insertions at the end, and using the head pointer or head reference, you can do insert and deletions from the beginning also. You can also use a circular queue to implement a doubly ended queue. A DQ can act as a stack or a queue. The idea is to maintain DQ in such a way that size of your DQ is K and front of your DQ stores the maximum of current window. So you can get the maximum in big O of 1 time. Please note that in DQ, all the 4 operations are big O of 1. You can implement all the 4 operations in big O of 1 using doubly linked list implementation of DQ. Using circular array implementation also, we can implement all the 4 operations in big O of 1. Let's now understand the working of this approach. Say we have this array. What we do is, we put the first item in DQ, we put 10. Then we put the next item in DQ 8. Then we put the next item 5 in DQ. Please note that I have written indexes also with the elements. In DQ, we are actually going to store indexes rather than elements so that we can figure out quickly whether the front of the queue has gone out of the window or not. Because if front of the DQ goes out of the window, we need to remove it, right? That's why we store the indexes. Using indexes, when we are at an index, we can figure out if front of DQ is useless for us because it's not part of the current window. So we first push 10, then we push 8, then we push 5. So we have added first window into the DQ. Now front of the DQ gives you the maximum. 10 is the maximum element in this DQ. So you are going to print 10 as output. In this particular example, our elements were sorted in decreasing order. Suppose our elements were like this, 5, 8, 10. Then the way we maintain DQ is, whenever we see an item, we remove all the smaller items than it from the DQ because they become useless. They are never going to become maximum in this window or subsequent windows where they are part of. So if our elements were 5, 8, 10, then we would have inserted in DQ this way. Initially, we would have inserted 5. Then when 8 comes, 8 would have removed 5 and we would have got 8 now. And when 10 comes, 10 would have removed 8 also. So we would have 10 at the end of these 3 elements, right? That's how we maintain the DQ. And that's the optimization we make. We try to keep minimum elements in DQ. We do not want to maintain any useless element in the DQ. So if our elements were sorted in decreasing order, the first 3 elements, we would have maintained DQ this way. 5 first, then 8, then 12. Only one element at a time. But here, in this example, the elements are sorted in decreasing order. So we keep all the elements because these elements might be part of upcoming windows. Because when you go to the next window, 10 is not part of the window. And if next window has an element 4, then 854 is the next window and 8 is the maximum element. So we need to keep smaller elements which come after. But when you see a greater element, you remove all the smaller elements from the array. So we need to keep the smaller elements when we see a smaller element, but when we see a greater element, we remove all the smaller elements from the end of the queue. So we are going to use DQ because we have these operations. We are going to delete from the beginning. We are going to insert an item at the end, and we are also going to delete from the end. 3 operations we are going to do. That's why we are using DQ, not a queue or stack. Let's see what happens when 12 comes in. And this is really interesting. When you process this element 12, your window size is 3. So using the index of this element in the window, your current window is this. Now you see a 12. So using the index of this element, you figure out that this element is useless. So what you will do, you will remove it because this is not part of the current window and it's never going to be part of any of the subsequent windows because it was the first element of first window. So you will remove 10 from this window. So now your window or your DQ is going to have 8, 5. Now you try to insert 12, and when you try to insert 12, you see that both of these elements are smaller than 12. So you are going to remove this from the DQ, you are going to remove this from the DQ because they are also useless. Why they are useless? Because we have seen a greater element. For current window, 12 is going to be the largest element. Even for the subsequent windows, they are going to be useless because 12 is going to be part of all the windows, all the subsequent windows where 8 and 5 are parts of, right? So for the next window, your 8 is not going to be part of the window, but 5 is going to be part of the window, but 12 is also part of the window, right? So whenever any of these elements, any of the previous elements are part of the window, 12 is also part of those windows. So these elements, these smaller elements than 12, they are useless now. So we remove them and we insert 12 into the D queue. Now we process the next element 15, and 15 is again greater than 12. Please note that 12 is part of this window, but 15 is smaller. The reason because of which we removed 8 and 5, because of the same reason we removed 12 also, because we have seen a greater element in the same window. So we are going to remove 12 from this window. Now when we see 7, we insert it. When we see smaller element, we insert it at the end of DQ. Now we see 6, we insert it at the end of the DQ because this is smaller. And after we have processed the first window, we are going to print the front of DQ because front is going to be the maximum. And when we process remaining windows, after doing the required insertions relations, we are going to do front again every time. So first we print 10, and when we did all the required deletions and then insertion of 12, we printed 12 also. And same for 15. After doing all the required deletions, insertions, we print 15. Same is for 7. After processing 7, we print 15, front of the queue. After processing 6, we print 15. So that's how we print maximums of all subarrays of size k. Now please pause this video and try to implement the approach yourself. Let us now talk about implementation of this efficient approach. In this implementation, we are going to use a DQ container. DQ is present in both C++ and Java. Here is C++ implementation, and this is how we create a DQ in C++. This is Java implementation, and in Java, DQ is an interface which is implemented by linked list class. So this is how we create a DQ in Java. Please note that in C++, DQ is implemented using array, but in Java, it is implemented using doubly linked list. We can implement our own DQ also. When we are implementing using doubly linked list, we just need to maintain front and tail pointers. When we are implementing it using array, we can use a circular array to implement it. In both the codes, we have two sections. The first section processes the first subarray of size k, right? This is the first section in Java code. Then we have the second section which processes remaining n minus k subarrays of size k. After we have processed the first subarray of size k, we process the remaining n minus k subarrays. When we process the current subarray, we remove the items which were there in the previous subarray but not in the current subarray. Now one important note about the namings of the functions in C++ and Java. In C++, we have function names as push front, push back, pop front, and pop back. Push front and push back, they add item at the front and back respectively. Pop front and pop back, they remove an item from front and back respectively. In Java, we have function names as add first, add last, remove first, remove last. Add first and add last add an item at the first position or front of the DQ, and add last adds an item at the last of the DQ. Similarly, remove first and remove last are used to remove items from first and last positions. To get the first item from the DQ, we have a function peek in Java. To get the last item from DQ, we have peek last. In C++, if you wish to get the front item, there is a function called front, and if you wish to get the last item, there is a function called back. Let's now understand these codes with this particular example. So we have an array of size 5 and we want to find out maximum of all subarrays of sizes 3. Now how many subarrays are we going to have? How many such subarrays we are going to have? We have one subarray this, then second, then third. Basically n minus k plus 1 subarrays. So as a first step, what we do is we create a DQ, as we have done in both the codes. After creating the DQ, we process the first window or first subarray of size 3. Basically, we process these 3 items. And when we are processing an item, we check if DQ last item is smaller than this item that we are processing. If it is smaller, we remove that because that item is going to be useless now. So when you begin with 20, there is nothing already in the DQ. So you are not going to fall into this loop because the first condition inside the loop is DQ is not empty, then don't enter. So we are not going to go inside the loop and we are simply going to insert 20. So when we say we insert 20, we actually insert the indexes of the items because we are using these indexes to decide which items are to be useless, right? So we insert the indexes. After inserting 20, we go to the next item 40. And this time DQ is not empty and last of the DQ is smaller than current item. 20 is smaller than 40. So we are going to insert 20 now. We insert the index of 40 and we remove 20, right? So we are going to have 1 now. Now we have processed 40, we are going to process 30. So when we process 30, last of DQ is greater, 40 is greater. So we are simply not going to enter inside this loop and we are going to insert 30. Index of 30 is 2. Now we come out of this loop and process remaining windows. We have processed the first window. Before we process the next window, we print the front of DQ. The DQ is maintained in such a way that items are always stored in decreasing order. Front item is the maximum. And how is this order maintained? Because whenever we add an item, we start checking from the end and we remove all the smaller items from the end and then we insert this item, right? This is how this order is maintained. So when you are processing this item, you print the maximum of previous window and maximum of previous window can be found at the front, right? So first thing we do is we print the front item or we print the peak item in array in Java. So what are we going to print after we are here? When we are here at this index, when I is here, we are going to print front, which is index 1, which is 40. So our output is now 40. After printing 40, we are going to remove the items which are not part of this window, whose indexes are smaller than or equal to I minus k. We are going to remove from the front this time, right? Because these elements are not part of the window. Now, if you see the front item, it's 40. It's part of the current window. So we are not going to enter inside this loop because dq.front is not smaller than or equal to I minus k. What is I right now? I is 3 and what is k? K is also 3. So 3 minus 3 is 0. Is not smaller than front. Front is 1, right? So we do not remove the front item. We do not enter inside this loop. Now we remove from the last. We remove all the items which are smaller and you can notice that the last item is index 2 item which is 30. It's not smaller. So we are not going to remove anything. We are going to come to this part or this part in Java and we are going to insert this item 10. Basically, we are going to insert its index 3. So that's our status of the DQ after you have processed last item of this window, right? Now we come to next iteration of the second loop and we are for I equal to 4. When you are at I equal to 4, what are you going to do? You are going to print the front of the queue. And what is front of the queue? It's 40. So your maximum of next window is also 40. You can notice it's 40 here, right? And after printing the front of the queue, what are we going to do? We are again going to check if the front of the queue is out of the current window or current subarray. It is actually out of the current subarray because this condition is true. So we are going to remove 1 from the DQ, right? Index of 40. Now our DQ is going to be 2, 3. And after removing it, we check if the last items of DQ are smaller than or equal to the current element that we are processing. So current element that we are processing is 60 and these both items are smaller. 30 is smaller and 10 is also smaller. So we are going to remove both of them. And we are going to insert the index of 60, which is 4. After inserting index of 60, we come out of the loop, right? Because this was the last element. And after coming out of the loop, we print the maximum of last window, right? And last window's maximum is also at the front. So we are going to print the front item or peak item in Java. So what is the front now? Front is 60. So last thing that we print on the screen is 60. Our output is 40, 40, 60 for this particular input. Let us now talk about time complexity of this implementation. When we take a first look at this implementation, it looks like more than linear because we have nested loops. But if we take a closer look, we can notice that every item goes into the DQ exactly once and comes out of the DQ at most once. So we are going 2 in insertions and removals, and insertions and removals at both the ends in DQ are big O of 1. Whether you are implementing DQ using circular array or doubly linked list, in both the cases, insertions and removal at both the ends are big O of 1 in DQ. So overall time complexity of this implementation is big O of n. Although we are doing 2 n operations, but that is also big O of n.